All right, everyone, I think I'll get started. All right, thank you all again for coming to this seminar. As always, I would like to start by acknowledging the traditional custodianship of lands on which the University of Wollongong is situated. We pay our respects to Aboriginal elders past and present, who are the knowledge holders and teachers. We acknowledge your continued spiritual and cultural connection to country. As we share knowledge, teaching, learning, and research within this university, we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of country. Our speaker today is going to be Ryan North, who is a PhD student here at UOW. He's going to be talking about his research on mapping the trace element zoning in zircon crystals using mass spectrometry. So let's welcome him up.
Thank you. Thanks everyone for coming. It's a great Friday afternoon to talk in grueling detail about reference materials and analytical methods. So yeah, thanks for coming. So this was a GeoQuEST funded project. Yeah, that was basically to establish uranium-lead dating here at UOW for zircon crystals. And secondly, to develop this new technique called TOF sims, which I'll introduce soon. So the project was semi-competent geochemical mapping used to evaluate zircon reference material homogeneity. That was supervised by Lloyd, Tony, and Mitch Nankaro from Innovation Campus. And I should also acknowledge some people for helping with sample prep, data collection, and just useful discussion. And that's Tim Murphy from Macquarie University, Jose, Don Turner, Alan Nutman, and Tim Barrows. Yeah, so let's get into it. Okay, so just some background. For those who might not know what zircons are, they're essentially a crystal, zirconium silicate, and they are these incredibly resistant crystals that persist in the geological record. They are usually really small, so that's something like a millimeter or less. Here we have an unusually large crystal. And essentially they're so useful for geologists because in their formation, they uptake useful trace elements that we can measure and gather information about the geological record. So one of those is uranium, which is radioactive and decays to lead. We can use that decay process to get an absolute age of the crystal. And that's been done before to date the oldest piece of anything on the Earth, which is a zircon, but also constrain the age of the oldest evidence of life on Earth, as well as just routine dating of igneous and sedimentary rocks. We can also look at hafnium isotopes in zircon crystals, which tells us about the crystallization history of that crystal, which you can trace back to the location of formation. So that's been used for reconstructing supercontinent cycles and understanding more about economic mineral deposits. But both of those can be used together as well for quaternary sediments. So if you find zircons in maybe a glacial, outwash, or fluvial deposits, you can trace back that sediment origin using the zircon chemistry. So super useful. We measure these with bulk and in situ techniques. A bulk technique dissolves the whole crystal and you get a really precise geochemical measurement. Whereas in situ techniques measure individual spots across crystals. This is more appropriate if you have complexly zoned crystals or in cases where there's limited material, you don't want to just dissolve all your samples. So that might be like earlier zircons or lunar zircons, for example. So in situ techniques require well-characterized, well-understood, well-known reference materials to get accurate results. So the initial question is, how well-characterized are those reference materials that we use and that important interpretations are based off? So I undertook a study of a database called GeoQuEST, where people report their measurements for the certain reference materials, of which I presented before here. And you can see that there is some elemental variation from what people report compared to the accepted value. The accepted value is that grey bar with the orange arrow behind each box plot. You can see that there's variation in almost all of them outside of that accepted value. And that's the same for isotopic ratios. People report, although the variation is less, which is good, but there's some variation. So that variation might be the result of inherent heterogeneity in our reference materials. And so that leads us to the aim of this project, which is to improve that characterization of those 4 commonly used zircon reference materials. And something that will feed back into that is developing this new technique, which I mentioned before, time of flight secondary ion mass spectrometry, which is TOF-SIMS, and that is a really high resolution mapping technique that we apply to the zircon reference materials. So here's just some optical photos of the crystals to show what they look like. 91500, it's a weird name, but that's just the sample name. It's a fragment of one large crystal that has been broken up and sent around to labs around the world that people analyze. Same thing for mud tank. We have fragments of a larger crystal. Tamora and Plesavice crystals are reference materials where it's actually just a whole lot of little whole crystals, so they're much smaller. But we also analysed zircons from Mount Dromedary or Gallagher down at the south coast near Tilba. You might have heard before. As we analyse them as like an unknown, just to test our methods. So I'll just briefly outline the methods. I'll explain TOF-SIMS, and then I'll show you what we got. So the initial characterization was what people normally do: backscatter electron imaging and cathodoluminescence imaging. Essentially, that gives you an indication of geochemical heterogeneity in the crystals, but doesn't actually tell you what chemicals are changing in the crystal. So this is like a first order image, I guess, that most people will do for zircon characterization. We then measured uranium, lead, hafnium, and trace elements and other trace elements in the crystals. So we used laser ablation and inductively coupled plasma mass spectrometry. So essentially, we have a laser, we ablate pits in the crystals. I think we did up just under 1,400 spot analyses across something 40 to 50 crystals. And that material that is ablated by the laser is then sent to a mass spectrometer, measured the isotope concentrations, and then we calculate some ages and trace element concentrations. We also made some raster maps by, instead of using the laser to ablate pits, we used the laser to ablate line scans across the surface of the crystal that were adjacent, and we stacked them up in some software to make a small image, I guess. That gave us trace element concentration maps. Time of flight SIMS, TOF-SIMS, does pretty much the same thing. It makes a a geochemical map, except it's much higher resolution than laser ablation mass spectrometry, and can detect more elements at once. So how it works is essentially you have an ion beam which ablates the very surface of your sample, so like nanometers of the surface, in this grid of spots which are like a couple of 100 nanometer size. That material is sent through a flight chamber, through a reflector to a detector in which all that material is detected. And so that theoretically can detect every isotope that's present, which is amazing in single analysis. And it separates those isotopes based on the time of flight. So lighter ions will travel faster through the flight tube, and heavier ones will travel slower. So it separates them out, but yeah, based on the time of flight. So you essentially get these high resolution geochemical maps. This is usually used in biological sciences or material sciences, and there's definitely less than 10, but maybe around 6 or 7 studies in the geosciences, of which this will be one, and just had another paper accepted for this applied on a course, which is awesome. Thank you. So yeah, incredibly new and powerful, and I'll show you what it can do soon enough. So yeah, this is just the initial characterization, so the backscatter images and photoluminescence images. And you can immediately see that for most crystals, there is some variation, some geochemical variation. The only one that was mostly homogeneous is 91500, which you might be like, hang on a second, I can see zones here. This light zone is actually an artifact from the machine, not from the crystal, and that's actually a pretty homogeneous crystal. So most of them have zones except 91500. I don't want to scare you with this amount of data, so let's just focus on 91500 to start with. These are the results from the uranium lead spot analyses. We gathered multiple spots on each crystal, and I presented them here as ages for each sample. And you can see that within each sample, so 91500 has 1, 2, 3, 4, 5, 6 different fragments. There is variation within individual samples. The mean of those is around the accepted age, which is that red line. But yeah, just note that there is variation within individual fragments. And that's the same pretty much for all samples. In some cases in like Mud Tank or Temora, the whole individual crystal is either above or below the accepted age. However, when you average them, we get some pretty promising results. So for 91500, Temora, Plesavice, and Mount Dromedary, when you get the mean of all of those spot analyses, it's actually within error of the accepted age, which is great. That's good to know for us. Except Mud Tank. Mud Tank's apparently 20 million years younger, which is bad for a reference material. And I think it's to do with the fact that we have a red-brown coloured crystal, which apparently aren't as reliable as gem quality colourless crystals that have been reported in the literature. So that's something good to know. If we look at the same for hafnium isotope ratios, again, a lot of data here, but what I want you to take away from it is that individual samples are variable. And some have quite a lot of variation, some have a little bit less. But in this case, it looks like Plesavice is actually quite good. And that's what we found, yeah. Plesavice, when you get the mean age, or the mean hafnium isotope ratio, it's within error of the accepted ratio. So that's a good reference material for hafnium. Temora and Mud Tank, the mean ratio was not within error of the accepted ratio, and 91500 wasn't either. But I'd just like to note that the accepted ratio is from a bulk analysis, and our analyses were obviously in situ laser-derived analyses. There was one study in 2005 by Woodhead et al., and they actually did a whole lot of laser analyses, and our result aligns with their laser results. So that's kind of good. Mount Dromedary, this is the first hafnium analysis on those crystals, so we can't really compare. But that's a new result anyway, and that's exciting in itself. All right. The detailed data is gone, the graphs are out. Now we can look at some pretty pictures of zircons, which is great. I'm going to show you the laser ablation geochemical maps, and then I'll show you the TOF-SIMS geochemical maps. So again, I have this 91500 crystal. Across the board, it was the most homogeneous. I'm showing you the one that had the biggest zone in it, I guess. The one with really the only zone. And you can see that uranium and rare earth elements like ytterbium and a few other elements were concentrated in dark CL zones. For mud tank, we see the same thing. Uranium, rare earth elements concentrated in dark CL zones. And ytterbium also has this little vein that's not in CL, so that's something to note. Tamora, again, we see the same thing, although I wanted to point out hafnium distributions don't align with CL, and pretty much for all reference materials, it was homogeneous. So that's also good. Plesavice, again, we see the same thing. What I wanted to point out here was that the parent radioactive isotopes like uranium and thorium, which decay to lead in our crystals, actually sometimes in the case of Plesavice and a few other crystals, don't match their daughter isotopes. So thorium-232, which decays to lead-208, you would expect them to be the exact same distribution because lead-208 doesn't come from anywhere else, usually. So we have a different distribution of those, and that's kind of unexpected and may be the cause of some of that variability in our uranium-lead ages. Something to maybe follow up on. And Plesavice also has these iron veins, which also have rare earth elements concentrated in them. There might be some secondary alteration. Dromedary, again, we see similar things. I just want to point out that dromedary crystals are really small, and when you get to this scale, the resolution suffers for laser ablation maps. As Tony described, it's like being in it's like looking at a 1990s video game, whereas TOF-SIMS is like a PlayStation 5 or something. And much better quality, high resolution images. So I'll show you the same crystals that we analysed with TOF-SIMS, and you can immediately see the resolution is so much better, although we couldn't pick up anything in that zone, so it looks like the detection limits aren't as good, at least for this crystal. But yeah, 91500 across the board, homogeneous in pretty much all elements. Mud tank, we saw elements zoned with CL again, things like scandium zoned with CL, and then we have other elements not zoned with CL. So something like magnesium and some other alkali elements were, I guess, in a distribution not visible in CL. So that's important. If you were going to measure trace elements in these crystals, TOF-SIMS can tell you exactly where they are instead of guessing from CL images. Here I want to show again, we have some trace element distributions in line with CL, but not necessarily. So we have these lithium zones perfectly correlating to the CL, but only in some sectors of the crystal. And you wouldn't know that from conventional imaging. And the same with ytterbium as well. Ceviche again, detection limits might have suffered a little bit. Looks like there's not a whole lot of signal from this one, but we can still see fine scale zonation in that lithium and uranium here in this dark CL zone. In dromedary, you can see really the power of the resolution of this technique, resolving uranium at, I think for this sample is less than 200 nanometer resolution, which is crazy. And also we see some hafnium fractionation in this specific crystal between hafnium 177, hafnium 178. It looks a bit weird just because I've filtered it to make it a bit more visible for this presentation. But yeah, that's something that was revealed from TOFSIMS. All right, so to bring that all together, to evaluate these reference materials so that we can use them for uranium lead dating, hafnium isotope ratios, trace elements. Here's the little cheat sheet I've made up. 91500 is probably the best. I recommend that as the best primary reference material for uranium lead isotopes. Tomorrow, Plezovice and Mount Dromedary are also fine. You just have to use many crystals and average them rather than individual crystals and trusting that they're within error of the accurate age. Mud tank, don't worry about it. Hafnium isotopes, Plezovice was probably the best one for that, although 91500 again is fine as long as you're using the laser-derived accepted value. Muntank and Temora weren't within error, so I can't recommend them. And Mount Dromedary, again, that's new, so probably need a bit more testing on that before we recommend it. The trace elements, as we saw in those maps, pretty much everything had zoning in it, so that kind of limits its use as a trace element, their use as a trace element reference material, because you want it to be mostly homogeneous. Yeah, so 91500 is probably the choice. In terms of the second aim of this project, summing that up, the development of this technique, we had some positives and negatives. Firstly, it's sensitive to a range of really useful elements in zircon, which is great. So uranium, thorium, hafnium, awesome. Got some rare earth elements as well, ytterbium, dysprosium, and some other elements like yttrium and scandium. And notably, it is very sensitive to lithium in zircon and in other minerals as well. So that's great. Its spatial resolution is among the highest resolution of any analysis of any mineral, which is crazy. Before excluding, imaging individual atoms with atom probe tomography, excluding that, it's among the highest of any analysis. And how we get that spatial resolution is by looking at the spot size plus the step size between spots. And so for this sample, it's just a little bit less than 2 micron resolution, but the best we achieved was just under 200 nanometer resolution. And just to compare that to other techniques, TOFSIMS image of the same crystal is comparable to electron microscopy, so BSE and CL images, and is much, much better than the laser ablation maps. These maps are created in less than 20 minutes, super fast to gather all that information, and it only ablates the surface 100 nanometers of the crystal, which is essentially non-destructive. You do more destruction with like one swipe of sandpaper. So it's conservative of your samples. Some negatives, it's only qualitative, so we can't actually straight up measure concentrations, only just relative concentrations. It is surface sensitive. So this is an example from quartz where the quartz surface wasn't perfectly polished. So any topological defects might trap contamination, and that'll show up in some of your trace element maps. And for zircon, it's unfortunate that we can't pick up lead isotopes. That would be really useful, but not only are they in such low concentration, I don't think the machine will be able to detect it, but also the fact that our ion source that ablates the stuff is a gallium ion beam, and gallium ions couple together in the machine and actually appear this exact same mass as lead-207. So I don't think, without changing the ion source, we won't be able to measure lead-207 ever. And the same kind of thing happens with hafnium-176. So that's a little bit annoying, but yeah, that's just limitation. So what's the future of this technique? I've described it as a really rapid, high-resolution zircon characterization technique, which I think, as more people get these machines, will become commonplace. And the fact that it's really, its resolution is similar to photoluminescence, maybe we could apply it and understand more about the origin of CL, because that's still controversial. And also potentially screen for lithium in old zircons, because lithium fractionation is a proxy for weathering of old zircons. So that's in zirconology, but this technique's been applied to quartz, I think serpentinite, diamonds, and pyroxenes. I think that's kind of it. So it's so new in geoscience, and I think like the power of measuring however many elements at once super quickly, relatively cheap, it has so many applications. So I encourage you to think how it might be applied in your research. Thank you.
All right, thank you, Ryan. Does anyone have any questions?
Where is the machine?
It's at the Innovation Campus. Yeah, the Electron Microscopy Center.
Any others? Yes?
Yeah, thanks. It was really impressive. Do you think there's any possibility, I mean, I know that you're not developing this whole machine, but do you think, can you imagine any way that surface sensitivity won't be such an issue? So I'm obviously thinking of teeth and not destructive.
Yeah.
Teeth for isotonalities.
It's a good question. I think the way we were going to try and get around it was being incredibly careful, obviously, in sample prep and polishing it like to the finest degree kind of thing. But also there's a technique, I can't remember what it's called, but you use like an ion mill to actually, so you put it in a machine and it uses like an ion beam to polish it essentially. And so I think that might be a way to get around it and get really flat surfaces. But I guess that's still going to destroy your teeth.
Yeah, but if you do it once, you should put it back together.
That's true. That's true.
All right. Anyone have more questions? All right. I've actually got one. So about the trace element variations within a single crystal, it's usually only related to depth, so it's in like concentric sort of zones.
Sorry, what do you mean? Like,
so does the trace element differ as you go deeper into the crystal?
As the laser ablates deeper?
Yes.
Yeah, it does, because the effectiveness of, I guess, isotopes coming out of the pit decreases as you get deeper. But in our data reduction, that is all accounted for.
Right.
So, yeah, I guess it's normalized that fractionation effect.
Okay. Well, if anyone has further questions, you're always...
Yeah, the people on the chat.
Yeah.
So, yeah. Coming off from the chat.
Blown up.
Oh, no, just people asking about... Yeah, they're not really asking questions.
You just don't want me to know.
Well, I mean,
Takeaways, hear me. Takeaways, hear me.
all right, well, Yes, if you want to.
I want to see the
Abuse.
compliments.
Right. Maybe I missed that at the beginning. Where did you get these reference materials? Obviously, like this is none of the research that I do, but it's super interesting. I was wondering, there's different research groups using the same materials. How are they being passed around?
Yeah, so those reference materials, except for Mount Dromedary, kind of, are like pretty well, at least Australia-wide, like used Australia-wide and if not internationally. So like that 91500 one is like a world standard. It's from Canada originally, I think. Tamora and Mud Tank are Australian, and I think Tamora's used a lot at ANU as a zircon standard. And then Plesovice is from the Czech Republic, and I think that's pretty widely used. Lloyd, you can confirm or deny that.
The source of where they were found is all right, but basically it's writing with people who developed the standard and asking for it. Maybe in some instances paying to get that. And depending on the reference material, there's some variation in costs of each one. Yeah. But 91500 is the kind of what every uranium lead laser lab uses as their primary reference material.
But the issue with that is also one day it will run out because it's just one crystal. It's just one big crystal that they found, smashing little bits off it. Eventually that will run out. So characterizing these other ones is also important.
Yeah, so 91500 is like found in a drawer in the New York Museum or something like that, and they're really not quite sure what actual. They know the region that it came from, but not actually the right spot. So it's very well characterized, but just not very well. It's basically irreplaceable. So.
All right. Well, if you have further questions, you're of course welcome to talk to Ryan as we enjoy the pizza and beer. Thank you again, Ryan.
Oh, no, I destroyed that.